Chapter 2 of our textbook focuses on forces acting on solid bodies. It also introduces the concept of a vector. In math and physics, a vector is some quantity that has magnitude and direction. For example, if you're flying in an airplane, you're traveling at 600 miles an hour, heading east-southeast. Your speed is 600 miles an hour. Your direction is east-southeast, and the combination of speed and direction is the vector that we call velocity. In statics, we use vectors to describe the force acting on a solid object along with the direction the force is acting in. Let's start by thinking about the forces acting on a heavy weight that hangs from the ceiling on a long string. The weight is pulling down on the string, so the string ends up with an internal force that is equal and opposite to the weight. We can draw a free body diagram of the weight using arrows to show the forces acting on it. Gravity is pulling the weight downwards, balanced by an equal and opposite tension force in the string. We call the force in the string capital P because it's a point force acting at a single point on the weight. The arrows in the free body diagram show us the direction of these forces. It's pretty obvious that the gravity is pulling downwards and the string is pulling upwards. The arrows in the free body diagram have four features. A force vector has a magnitude, a direction, a sense, and a location. The magnitude is the size of the force, in this case 40 pounds. Units could be newtons in the SI system or pounds in the US customary system. 1,000 newtons is 1 kilonewton. 1,000 pounds is called a kip, which is short for kilopound. A US ton is 2,000 pounds. The direction of the force lies along a particular line. The sense tells us which way along the line the force acts. We use an arrowhead to show the sense. The location where the force acts is at the head or tail of the arrow. Some forces are applied along the length of a beam or over an area of a roof. We call these forces distributed loads. One example of a distributed load is the weight of snow on a roof in the winter. Another example is the weight of a long beam measured in pounds per linear foot or newtons per linear meter. For example, a 2x4 timber made of white pine weighs about 1.5 pounds per linear foot. What if two forces are at right angles to each other and they act on the same point? You'll see these forces labeled as either orthogonal or perpendicular forces. Both words mean the same thing. Orthogonal is derived from the Greek, while perpendicular is derived from Latin. We can calculate an equivalent force called a resultant force that equals the effect of the two combined forces. In this diagram, F sub x and F sub y are the horizontal and vertical forces, and capital R is the resultant force. Here, we can use geometry and trig to solve the problem. The Pythagorean theorem helps us find the resultant force. Take the square root of both sides, plug in the numbers in units, and the resultant force is 104 newtons. Use the inverse tangent to find the angle theta off the x-axis is 35 degrees. We can go the other way too. Given the resultant force and the angle theta x, find components f sub x and f sub y using trig. First, use the sine function to solve for s sub y is 19.7 pounds. Next, use the cosine function to solve for f sub x is 37.1 pounds. What if we're given the resultant force and the pitch? In building construction, the roof pitch is rise over run. So a 3 in 12 pitch means the roof rises 3 feet for every 12 horizontal feet. We use pitch for wheelchair ramp design, typically 1 in 12. When you drive over a mountain pass, road signs tell you the percent grade of the slope, and that's also a measure of pitch. A 6% grade is a 6-foot rise for 100 feet of forward travel. In this case, we can use similar triangles to find f sub x and f sub y. Notice the resultant force is shown as F instead of R. It really doesn't matter what the label is. You'll see it both ways. Here, the pitch is 2 in 5. So we can draw a similar triangle with height 2 and base 5. Using the Pythagorean theorem, the hypotenuse is the square root of 29, about 5.39. Now let's use similar triangles. The ratio of the lengths of any two edges of one triangle is the same as the ratio of the lengths of the same edges of the other triangle. Set f sub x over f equal to 5 over h. Set f sub y over f equal to 2 over h. Now we can rewrite the equations and solve them to get the final answers. Could we have used trig instead? Sure, but it takes more steps. Sometimes trig is faster, and sometimes similar triangles is faster. Let's talk about axes. Usually the x-axis is horizontal and the y-axis is vertical. In some problems, the math is simpler if we pick different axes. For example, it's easier to do the math for a block on a slope if we take the x-axis along the slope's surface and the y-axis perpendicular to the slope. The reason the math is easier is that there are 3 forces acting on the block: gravity, friction, and the normal force exerted by the slope. 2 of these 3 forces are oriented to the slope. Friction acts along the direction of the slope, and the normal force is perpendicular to the slope. The free body diagram shows these forces acting on the block. We're going to solve problems like this later in the course. The last important point in this chapter is the sign convention. In this textbook and in most other statics textbooks, forces acting upwards and to the right are positive, while forces acting downwards and to the left are negative. That's all for now. Next time, we'll start on Chapter 3.